Hello and welcome to this lecture on advanced electric drives. In the last lecture we are discussing about the hybrid stepper motor. The objective is to get more torque and a small step size. Now in hybrid stepper motor, the torque is produced by the combination of variable reluctance torque and the permanent magnet torque. And the cross sectional view of a hybrid stepper motor is shown in the following figure. In this case we have the stator, this is the stator section, we have taken a longitudinal section, we have a stator here, and the stator has got two blocks in this case, and this is also the stator. So, we have the stator here also. So, this is also the stator, and the rotor also has got two blocks, one in the left hand side, other is right hand side, and we have the shaft, this is the rotor shaft, and the stator carries winding. In fact, the stator is also having slotted structure. We know that in case of stepper motor there are teeth and slots. The stator has got also teeth and slots, the rotor also has got teeth and slot, but the stator carries winding, and in this case the stator carries concentric winding. So, what we have here, this is basically the windings here. So, if we, so this is the winding we have, this is one winding, and then we have the winding overhangs here, these are the winding overhangs, these are also the winding overhangs, and here also we have the winding overhangs in this case, and they are called concentric windings. And what we have in case of the rotor has got a permanent magnet and it is an axially polarized rotor. So, we can say here this is an axially polarized rotor, axially polarized. How is it polarized axially? Now, we know that we have two blocks of the rotor, and if we go on putting permanent magnet across the rotor surface, it will be a big task. So, we do not put tiny magnets over the surface of the rotor. What we do instead, we put bar magnets along the rotor shaft, so that one side is north pole and the other side is south pole. So, what we have done here is this, that this is the magnet that we have placed here, and this is actually a magnet along the shaft of the rotor. So, this side is the south pole and the right side is the north pole, and hence we can plot the flux lines. The flux line will come out of the north pole and enter the south pole. So, this is the flux lines in this case through the stator yoke. So, this is how the flux lines will pass. Similarly, on the other side we have the flux lines in the south pole and the north pole. So, we have the flux lines which is coming out of the axially polarized magnet, and here the north pole is on the right hand side. So, this is basically the flux line will come out of the north pole and will enter the south pole, and this enters the south pole like this. Similarly, on the other half we have the north pole, the flux lines will be coming out of the north pole, will be like this. So, these are the flux lines and they will be entering the rotor block, and this is how this enters. As a result, if we see, one half of the rotor is the south pole and other half is the north pole, because when the flux is entering the rotor it is a south pole, when the flux is coming out of the rotor it is a north pole. So, we have not placed tiny magnets across the surface of the rotor, we have put the bar magnets, and as a result the entire rotor block in the left side is south pole and on the right side it is north pole. We can see here this is the south pole, we have a south pole in the left side because the flux is entering the rotor, and on the right hand side we have the north pole, the flux is coming out of the rotor. Now, how is the torque produced? Now, let us assume that in this case the stator has got 4 poles. If the stator has got 4 poles, we can show the pole structure and show the windings, and the pole structure is shown as follows. So, we have the pole structures which we can show here, that if we show a structure of the stator, this is the stator surface, in the left side. So, we have 4 poles here. So, and this is the rotor. So, 4 pole means we have 4 projection in this case, and the projections could be like this. This is 1 pole, second pole, the third pole, and the fourth pole, so this is the rotor inner surface, the stator inner surface, and this is the stator outer surface. What about the rotor? The rotor carries slots, and the rotor in fact carries slots and teeth, and the slots and teeth are so arranged that sometimes we have a slot, other times we have a tooth, and so on. And in this particular situation we can show, for example, here we have the structure like this. This is a tooth and this is a slot. We show the slot like this and tooth like this, and the stator we have the 4 poles, and these carry windings and this carry physical concentric windings, and similarly this also carries winding, and these windings are all connected, series connected. So, this is phase A, we can call this to be A1 and A2, and similarly in this case we have the windings here, this is B1 and it is wound like this, this is B2. So, the stator carries concentric winding that we have already shown here, and these windings are shown in the following fashion. So, this is A1 and A2, B1 and B2, and then when we talk about the rotor slots and teeth, when we excite phase A1 and A2, we can excite in the following sequence. We can excite A1 A2, B1 B2, A2 A1 and B2 B1. So, in this following way we can excite. So, we can excite like this. First of all we can excite A1 A2 and then B1 B2 and then A2 A1 and then B2 B1, and then it repeats. So, we can start again with A1 A2. When we see the tooth and the slot arrangement, we see that this is the phase A is facing a tooth. So, this is a tooth and phase A2 is facing a slot, and when we excite that particular phase we create a north pole. In fact, this entire block is actually south pole. So, we can say that this is the south pole, the left side of the rotor, as we have seen here that the left side is entirely south pole. So, we are in fact plotting the cross section of the left side of the rotor. So, the left side is entirely a south pole. So, we have shown the south pole, and in the south pole when we excite phase A1 and A2, we create a north pole under A1. So, what we have here is that we have north pole here and then we have a south pole here. When we excite A1, A2, we create a north pole under A1 and south pole under A2, and A1 is facing a tooth and A2 is facing a slot. What about B1 and B2? B1 is neither facing a tooth nor facing a slot. So, we have a situation like this, that in this case the tooth is here and the slot in this case is like this. So, if we see the phase B1 and B2, B1 is neither facing a slot nor facing a tooth, and B2 is also neither facing a slot nor facing a tooth. Now, right now when we change from A1, A2 to B1, B2, what happens? Earlier A1 was north pole, and now when we shift from A1, A2 to B1, B2, B1, the phase under B1 will become a north pole. So, when B1 becomes a north pole, the rotor will try to move, and try to move by what angle? Such that the B1 phase will see a tooth. So, in this case we can see here when it moves towards the in the anti-clockwise direction like this, when we excite B1 and B2, we will have a north pole here. So, if we have a north pole here, this north pole will attract the south pole tooth. So, this will be moving in the anti-clockwise direction, and finally this tooth will be coming fully under B1, and hence the movement of the rotor will be by 1/4 of tooth pitch. By tooth pitch we mean we have in fact we have a tooth like this and a slot like this. Basically these are the tooth and slot structure. We have so many teeth and so many slots. So, when we excite phase B1, B2, the movement will be by 1/4 of the tooth pitch. So, this is basically 1/4 of tooth pitch. What is the tooth pitch? The tooth pitch will have one full tooth and one full slot. So, this is one tooth pitch, this is one tooth pitch. One tooth pitch is made of one full tooth and one full slot, and when the movement is by 1/4, this is 1/4 of tooth pitch. So, this is how the rotor will move, and when it moves in the anti-clockwise direction, when we excite phase B1 and B2, a tooth will be under phase B1, and then after that we will be exciting A2 and A1, because we have to go in a sequence. We have started with A1, A2, then B1, B2, then we have to again go back to A2, A1, so that A2 will become a north pole and A1 will become a south pole. Now, north pole will always attract a south pole tooth. So, if we excite A2, A1, after B1, B2 we will be exciting A2, A1, what happens? It means when we excite A2, A1, this is A2 and this is A1. So, we have A2 phase is here, A1 is here. When we excite A2, A1, this is already moved by 1/4. So, in fact A2 is now facing, when B1 is excited, A2 is basically facing neither a tooth nor a slot, it has the edge of a tooth. Again when we excite A2, A1, the tooth will come in, and again the movement will be by 1/4 of tooth pitch. So, here the step size is basically 1/4 of tooth pitch. So, when we excite, say for example, when we started with A1 A2 the angle was 0. When we have excited B1 B2 it moves by 1/4 tooth pitch, and then we have excited A2 A1, it further moves in anti-clockwise direction by 1/4. So, 1/4 of tooth pitch, and then we again excite B2 B1, it moves by 1/4 of tooth pitch, and then again by A2 A1 it completes 1/4 of tooth pitch. So, here what is the step size? The step size is in fact 1/4 of a tooth pitch. Say for example, in the rotor we have, let us say, 60 teeth. So, if we have 60 teeth in the rotor, what is the step size? 360 by 60 by 4. So, say for example, we can take an example here. Rotor number of teeth is equal, let us say, we can say it is 60. So, if 60 is the number of teeth in the rotor, what is the step size? The step size will be basically 1/4 of the tooth pitch, and tooth pitch here, one revolution is 360 degree. So, 360 by 60 is 6 degrees, and 1/4 of that is 1.5 degrees. So, step size here is 360 is the complete revolution, one circle, by 60 is the number of teeth in the rotor. This is the tooth pitch, 1/4 is the quarter of a tooth pitch, and that is equal to 6 degrees by 4, and that is equal to 1.5 degrees. Now, it is so interesting that without increasing the number of poles, we have only 4 poles in the stator. We are not increasing the number of poles in the stator, we have only 2 phases, A1 phase A and phase B, A1 A2 and B1 B2. But what we have done, we have placed a magnet in such a way that 1/2 of the south rotor is the south pole and other half is the north pole, and by doing that and by increasing the number of teeth and slot, we are able to have a reduced step size. In fact, the step size can be further be reduced if we increase the number of teeth. So, here we have the step size is equal to 1.5 degrees. Now, we have seen actually 1/2 of the rotor. What happens to the other half? So, we have 2 sides. One side is in the left hand side, and other side is the right hand side. So, in fact, what we can see here, that if we see the structure of the stator and structure of the stator here, they are something very similar. What about the rotor structure? This is the rotor, and here also we have the rotor, and we have 4 poles here, one pole, the second pole, the third pole, and the fourth pole, and similarly here also we have 4 pole structure, 1, 2 and 3 and 4, and this will carry windings. This all will be carrying windings here. This also will be carrying the windings. So, in this case, how does these two placed with respect to each other. Now, we have a left side and we have a right side, because we understand that in this case the rotor has got two blocks. The left block is entirely south pole and the right block is entirely north pole, and the stators are also connected like this. The stators will be excited in a similar fashion. In fact, when we say A1, A2, all the stators are excited at the same time, and when we say B1 and B2, the stators, the left side and the right side, are excited at the same time. So, this stator is A1, this is A2, this is also A1 and this is A2, having the similar windings. We have B1 here and B2 here, this is also B1 and this is also B2. The difference comes in the rotor. The rotor left side is entirely south pole. So, what we have here is that this is entirely south block, and then the right side rotor is north pole. This block is entirely north pole. So, this is called a homopolar structure. It means the whole of the rotor in the left side is south pole, the whole of the rotor on the right side is a north pole. Now, when we excite A1, A2, a north pole is created under the stator also. So, the stator is north pole here. Now, this is the north pole in this case. When we excite A1, this becomes a north pole, this also becomes a north pole, and A2 becomes a south pole, this also becomes a south pole. Now, when we talk about the rotor teeth in the left side, here we have a teeth, we have a tooth here and we have a slot here, and this is neither facing a tooth nor facing a slot, something like this. What about the right side? Right side, again this is a north block. So, this should be a slot and this should be a tooth. So, if we see the right side rotor block and the left side rotor block and try to compare this, the tooth and slot structure, they will be opposite of each other. In fact, the slot of the left side is aligned along a tooth of the right side. The tooth pitch of the left side and the right side are the same, but they are offset by half a tooth pitch. It means the slot of the left side is coinciding with the right of the right side, tooth of the right side. So, in fact, they are offset by half a tooth pitch. So, if we are to show the entire structure like this, rotor structure, if this is a tooth and this is a slot like this, in the left side, in the right side what we have is the following. Right side we will have the structure here, we have exactly a slot here and we have a tooth here. So, it means a tooth is matching with a slot of the right side, a slot of the left side is exactly coinciding with the tooth of the right side, and this is entirely a south pole block, this is entirely a north pole block. So, if we see the right side once again, we see that when we excite phase A and A2, north pole is under A1 and south pole is under A2. So, the tooth of this is attracted by the south pole structure here. So, that also is conducive for the torque production. So, in this case the two blocks are offset by half a tooth pitch. Now, this is how we have the combination of both permanent magnet torque, also the variable reluctance torque. Now, to further enhance the torque, the stator structure we have shown in terms of very smooth poles. The stator structure, although we have only 4 poles here, the pole shoes are corrugated. Pole shoes are not smooth as we have shown here, they are also corrugated to match with the corrugation of the rotor. So, in fact, if we draw the structure of the stator pole, it will be something of this sort. We can draw a stator pole structure, it is having slot and tooth. Here we have a tooth and slot again, tooth and slot, tooth and slot, tooth and slot, tooth and slot like this, and this is how a pole looks like. And these are so planned that the rotor will be exactly under this. We are drawing the rotor structure, and hence there is a perfect locking. This is the rotor surface, and here we have the stator pole, and we have the windings in this case. The stators actually carry the windings, but the stator pole is not a smooth pole, it is basically corrugated, having slots and teeth in such a way that tooth of the rotor is facing the tooth of the stator and slot is facing the slot, and hence there is perfect locking, and thus we can have a high detent torque. Not only that, when we excite the stator, the torque production is basically due to the permanent magnet torque, also due to the variable reluctance torque, and hence we call this to be hybrid motor, hybrid stepper motor. The hybrid stepper motors are very popular because of low stepping size, step size is very, very low. Also the torque is also enhanced. One drawback of variable reluctance stepper motor is that there is no detent torque. By detent torque we mean when we excite the stator, there is a torque production, there is a locking mechanism, but when we do not excite, the torque is 0, and this torque is 0 for a variable reluctance type of stepper motor, but this torque is not 0 for a hybrid stepper motor. In hybrid stepper motor, the torque is still present because of the permanent magnet in the rotor, and hence we have a detent torque. Now these are the various type of stepper motor we have studied. Primarily there are 3 types of stepper motor. To summarize, we have variable reluctance type stepper motor. We can increase the step size by increasing the number of stack. We can have a single stack or a multi stack motor. Then we can also have a permanent magnet stepper motor, where we have the torque produced only by the permanent magnet, and finally we have a hybrid stepper motor where the torque is produced by the combination of permanent magnet and variable reluctance type of torque. Now having discussed about the structure and the type of stepper motors, we will discuss about the behavior of stepper motor. Now let us have a look at the stepping rate. Now the stepping rate we define as the number of steps per second. So that is the definition of stepping rate, and if we increase the stepping rate, the speed increases, and beyond certain stepping rate the stepper motor does not stay in synchronism. Stepper motor is a very beautiful motor for position control. We do not have to have any position feedback. What we give here is a few pulses, and the rotor faithfully obeys these pulses, and hence the position control is achieved without any closed loop feedback. Stepper motor control is primarily an open loop control, and hence it is much more attractive compared to a servo motor. In servo motor we have to have a closed loop position feedback. In stepper motor we do not have to have a position feedback. We apply the pulses, and the rotor follows the number of steps. But if the stepping rate is increased, the motor falls out of synchronism. It does not faithfully obeys the stepping command, and we have to confine the operation within a acceptable stepping rate, and that is how we can determine the operating range of the motor. Now we can draw a graph which will give us the load torque versus the stepping rate in second. So this is pulses per second, and the load torque could be in Newton meter, and we have two types of characteristic, and this is basically what you are trying to draw here is torque versus stepping rate characteristic. And here what we have here is that we can have two types of graphs here, one is like this, other is like this. So, this is origin we have, and suppose we apply a load torque, and the load torque here is TL1. Now, the first curve we can show this by 1, and this is the second curve we can show this by 2. So, this is the first curve and this is the second curve. So, we have two curves here, curve 1 and curve 2, and if we have a load torque and the load torque is let us say TL1, we will have two stepping rates corresponding to 1 and corresponding to 2. What does it mean? Here we have two stepping rates here, this will give us S1 and this will give us S2. Now, this S1 is the stepping rate for which the motor should be starting. When the motor is under standstill condition, we can maximum give a stepping rate that is equal to S1 to start the motor. And once the motor starts, you can increase the stepping rate to S2. So, the starting stepping rate should be below S1, and once the motor starts up, you can increase the stepping rate to S2, and hence we can call this graph 1 to be the start graph or the starting graph, and the graph 2 should be the running. So, we can say that the starting stepping rate should be less or equal to S1, the running stepping rate should be less or equal to S2. So, this is for a load torque, for a given load torque, what is the load torque here? Load torque is TL1. So, for a given load torque TL1, to start the motor, the stepping rate should be less than S1. What happens if you apply more than S1? Say for example, S1 is 3000 pulses per second. If I apply 350 pulses per second, what happens? The motor will not respond, motor will refuse to start. So, for starting of the motor, the stepping rate should be less than S1. The motor is under standstill condition, it is having some inertia. So, to start the motor, the stepping rate should be a low one, and once the motor starts, you can apply a higher stepping rate, that is up to S2. So, we can call this to be the slew range. So, this green colored region, we can call this to be the slew range, and the region which is left of 1, which we can show by let us say this blue graph, this is called the start range. It means if you want to start the motor, the stepping rate should be in the start range. So, after the motor has successfully started, you can increase the stepping rate to the slew range, and it should be under no situation should be on the right side of second characteristic. If we go beyond this, suppose we have the stepping rate which is here, and for this stepping rate motor falls out of synchronism, motor does not stay in step and the position control is lost. So, we have to be very careful that for starting of the motor, the stepping rate should be in the start range, and when the motor runs, we can operate, the stepping rate can be increased to the slew range. So, this is how the stepping rate is determined for a given load torque. Now, when we have a stepper motor drive, we require a drive for that. We want to have a converter which can inject current into the various windings. So, we can have a simple structure in which we can inject the current onto the various phases. Unless we excite the various phases, motor will not start. So, we have to have a converter to inject the current onto the windings of various phases, so that the motor starts. And hence, we can have a variety of converters which can be used with a stepper motor. So, let us see one type of converter. So, we will have the drive circuit for stepper motor. A very simple drive circuit. What we can have here is the following: we have a DC supply, and then we have a switch, and then we have the phase of the stepper motor, the winding. Of course, we have to have a freewheeling diode. So, this is the voltage that we have, Vd, and we have the phase, and we can have the current in the phase, that is I phase, and this is the freewheeling diode we have, that is Df. So, this is the simple circuit for a stepper motor drive. We have a DC voltage, we have a switch here, we have the winding, and then we have a freewheeling diode. Now, what is our ideal characteristic? When we excite a stepper motor, the current should rise very sharply and reach the maximum value, because current determines the flux, determines the MMF. Hence, the current should be essentially a rectangular current. So, what we have here is the following, that this is our ideal characteristic. We want our characteristic to be ideal. So, this is the time axis, and this is the axis of I phase. So, this should be the ideal characteristic. So, this is the ideal current. So, the actual current, however, does not follow the ideal behavior. So, the actual current rises like this, reaches the maximum value, and then when we close the switch, the current rises, reaches the maximum value, and it stays there, and then when we want the current to be equal to 0, we switch off this switch. We have a switch here, this is turned off, and when we turn off this switch, the current freewheels through the diode Df, and this decreases. In the freewheeling process, the current decreases. So, what we have here is that the current falls like this. So, this is how the current in a winding changes, but we want the ideal behavior. So, we can improve upon this particular circuit to achieve a ideal characteristic, and that will be seen subsequently. We are discussing about the drive circuit of the stepper motor, and we know that we want an ideal behavior of the current. Whenever we close the switch, current should rise to the finite value. When we open the switch, current should come back to 0, but it does not happen in practice. In fact, every winding is having some inductance, every winding is having some resistance, and hence when you close the switch is closed, the current is going to take some time to rise, and this rise time can be reduced if we reduce the time constant of the circuit. Similarly, when we switch off the switch, the current will fall down to 0 by freewheeling through the diode. So, we have this diode here, and the current in fact freewheels when the switch is off. The current freewheels like this, and because of the freewheeling it takes some time for the current to come down to 0. So, we have the rise of the current is like this, then it stays at the maximum value, then when you switch off the switch the current comes back to 0. And can this rise time and fall time be reduced? The rise time and the fall time can be reduced by a simple means: insert a resistance. Insert a resistance in the winding during the on state of the switch and insert some resistance in the freewheeling diode during the off state of the switch. So, what we do here is the following: we insert some resistance here, maybe we can call this to be R1, and we can also insert some resistance here, that is R2. So, by inserting resistance, what we are trying to do effectively, we are trying to reduce the time constant of the circuit. If the inductance is, say for example, the time constant is given by tau is L by R, and that is equal to L by the resistance of the phase plus R1 in the on state, and in the off state this is the on state time constant. In the off state we have the time constant equal to L by, it is freewheeling like this, this is R phase plus R1 plus R2 plus the diode resistance. So, this is the off state time constant and on state time constant is L by R phase plus R1. So, by introducing resistance in the respective circuit, we can minimize the time constant and hence we can reduce the on time and off time. This is one of the techniques followed to minimize the rise time and fall time of the current in a stepper motor drive, very inexpensive. But what is the problem? The problem is that the drive is going to be less efficient, because whenever we insert resistance it is going to consume power. The overall efficiency is going to come down. So, we can of course we can increase the fastness of the circuit, the rise time and the fall time can be reduced definitely, but at the cost of the efficiency. So, by introducing the resistance we can perhaps increase the fastness, we can say that the rise time improves and the fall time also reduces, but this will be less efficient. So, the efficiency goes down. Now, what is the solution? The solution is to go for an efficient drive. In an efficient drive, we can apply sufficiently high voltage so that the current rises to the maximum possible value. Now, in the rise time, if we see, the rise time is not only a function of the time constant, but also a function of the applied voltage. So, we can apply little higher voltage so that we get a faster rise time, and then when we want to make the current equal to 0, instead of freewheeling the current, we feed the current back to the source, and that means the energy of the inductor is not wasted, it is fed back to the source, and that is an efficient drive circuit which can be employed for stepper motor. So, we will be discussing about an efficient drive circuit for stepper motor. So, an efficient drive circuit Now, what we have in this case is applied voltage, and then we have two switches here. We have the phase in this case, we have another switch here, we have the diode here, So, this is S1, S2, D1 and D2, this is a phase, V phase here, and this is I phase. Now, this operates in an interesting way. When we want the current to be established in the winding, we switch on S1 and S2. So, when S1 and S2 is switched on, the voltage across this winding will be VDC, or the applied voltage. So, this is VD or VDC, this is applied voltage. So, suppose we want the current to follow a particular pattern. So, this is our ideal current, it should be something like a rectangular structure, and this is the time axis, and this is I or I phase. So, we switch on S1 and S2, the current rises here, and then we switch off S2, one of the switches is turned off. When the switches is turned off, the current falls down in this case, and then we switch on again S2, the current rises, and then we switch off S2 and the current goes on changing like this, and finally, when you want to bring the current down to 0, we switch off both S1 and S2 and the current falls down to 0 like this. So, this is the nature of the current in the winding or the phase of the stepper motor. So, if we plot the corresponding voltage here, the applied voltage in this case so when you want to, when the current builds up, we apply VD, we turn on in fact S1, S2, then we switch off S2, it freewheels through the freewheeling path is like this, S2 is turned off, S1 is still on. So, this freewheels here, the voltage is 0 in this case, then again we turn on S1, S2, it goes down to 0 again. So, the voltage changes like this. So, this is how the voltage changes. So, here what we do, we apply again positive voltage, and then when you want to finally bring down the current to 0, a negative voltage is applied. So, in fact, the conduction sequence is as follows: S1, S2, then S1, D1, S1, S2, S1, D1 and so on, S1, S2 and S1, D1, and finally, during this time the conduction is fully by D1, D2. So, when we turn off both S1 and S2, the current is still in the winding and any inductance will try to maintain the current, and when we switch off S1 and S2, the current tries to flow through D1 and D2, and in that process it is fed back to the supply. So, the current does not freewheel, the current in this case is fed back to the supply like this. So, this is how the energy in the inductor is not wasted anywhere, it is ultimately fed back to the source. So, this is definitely an efficient drive. In some situation, as we have already seen in case of say for example a hybrid stepper motor, we need to have a bipolar drive. So, this is an example of a unipolar drive. By unipolar drive we mean we are primarily applying a positive voltage. So, this is an example of a unipolar drive. So, we have primarily this is a unipolar drive. When we go for a hybrid stepper motor, there is a need of a bipolar drive. In bipolar drive, both current should be reversed. We can have A1, A2 and then we should be able to have A2, A1. So, that can be achieved by having 4 transistors. In this case, when we have a unipolar drive, we have only 2 transistors, transistor S1 and S2, we have the switches S1 and S2. Now, if we want to have a bipolar drive, we have to have 4 transistors S1, S2, S3 and S4 as follows. So, we can have a bipolar drive bipolar stepper motor drive. So, what we have here is the following: we have the applied voltage here, and we have 4 transistors. It could be any transistor, maybe MOSFET or BJT. It is a small drive, it is a low power drive. So, we do not have to use very high power devices, it could be primarily MOSFET. Although we have shown the symbol of BJT, these transistors, and then we have the feedback diodes. The diodes are inherently present here. They will help us in freewheeling or feeding back the current. And we have the windings in this case. This is, say for example, A1, A2, this is the V phase with plus and minus, this is I phase. So, we have S1, S2, S3 and S4, and we also have D1 and D2, this is the feedback diode. So, we have 4 diodes and 4 transistors here. So, this is applied voltage. So, to apply a positive voltage, we switch on S1 and S2. Positive voltage is applied by turning on S1 and S2. So, that is Vd. And we can apply a negative voltage by turning on S3, S4, and that is equal to minus Vd. So, this is how we can apply either a positive voltage, we can apply voltage to A1, A2 when we switch on S1 and S2, and when we want to apply a negative voltage, we can switch on S3 and S4 and we apply minus Vd. So, this is how we can excite the windings of a hybrid stepper motor, where we need to reverse or we need to apply positive and the negative both. We have already seen that the sequence of the switching is A1, A2, B1, B2, A2, A1 and B2, B1. So, we have to go in that particular sequence. So, if we apply positive voltage for A1, A2, for A to A1 we have to reverse the voltage, and that is achieved by switching the other pair of transistors. Now, this is how the winding of a hybrid stepper motor can be energized. So, we have seen simple drive circuit for stepper motors. The drive circuits can be unipolar for simple stepper motor, and that could be for variable reluctance type stepper motor. For permanent magnet and hybrid stepper motor, where we have the permanent magnet, whenever we have a permanent magnet, current direction matters. We cannot be applying only in one direction, we have to have a facility for bipolar power supply, and hence the bipolar stepper motor drive are suitable for permanent magnet and hybrid stepper motor. So, this completes our discussion on stepper motor. We have seen various type of stepper motor, starting from variable reluctance type stepper motor to hybrid stepper motors, and each one is having its own advantages. So, finally, the best possible stepper motor could be the combination of the two, that is an hybrid stepper motor, where the stepping size or the step size can be reduced to a very small value without any difficulty. So, in the next lecture we will be taking a new type of drive, the application of induction motor drive, and how we can have a utility friendly drive which can be applied for high power application like traction, and what is the effect of the drive on the power system, how we can improve the quality of electric power while operating the drive. That we will be discussing in the next lecture.